Hi, my name is Vinod Halaharvi. Thanks for listening to my project. So I would like to compile and run my project. Let's compile this project. Okay, and let's run it now. Okay. As you can see here, I'm using communication port 6, serial port 6. So I'll bring up the secure CRT and use the serial port. And as you can see, I have a shell prompt here. So I can type help. That'll show all the commands I have. Just a simple echo command. Okay. ls command. Right now, I don't have any files in my file system. I do have the device files initialized, but I don't display those to the users. So when you type ls, only the regular files get displayed. So as you can see, there are no files right now. So I can create some files using the Unix like touch command. So as you can see, 15 is the file descriptor for file 1, and 16 is for 2, and 17 is for 3, and so on. Now the output of the ls command, you can see the inode numbers. The inode numbers for this operating system starts with 0, and the R here stands for regular file, and these are the file names. So my final project is creating hard links and soft links. So I would like to demo the hard and soft links now. So first of all, let's create a soft link. I'm using the Unix style ln command to create the soft link. ln with -s option. S stands for soft link, and then I give the link name. Then I give the file name. Okay, and if I similarly I can create a hard link as well. -h is the option for hard link. Okay, now if I do a ls, I have these two links created. Now if you see, when I created the hard link, the link count got increased for the original file by 1. So the total link count right now for 1 is 2, because only the hard link increments the link count. That's how I track when to release the resources for the file 1. And soft link, there is no increase in the link count. The other thing we can notice here is the hard links inode number and the original file's inode number are the same. So that's how I kind of keep track of the hard links and the regular files. But for the soft link, the inode number is different, and the binding happens purely based on the name, file path, for both the link and the original file. Okay, so now let's write some data to the file. I have a helper command called toFile. I give the file descriptor number and some sample string that I want to write to a file. Now I can run a cat command to see the data that I wrote to the file right here. Now I can also run that cat command and on the soft link, which will also give me the same data again, and also on the hard link. So let's write some more data to the file. Now I can see either by the hard link or by the soft link, same data, or I can see from the original file also. Okay, so I would like to move on now and demo the pseudo parallelism for my operating system. So as you can see on the right top corner, I have 3 LEDs to demonstrate that. Please ignore the blue LED, it's not doing anything. But the orange LED, yellow LED, they blink at the same frequency, and the green LED blinks at like 1/10 of the frequency of the orange and yellow. There is no specific reason, I just use those frequencies just to demonstrate the program. So one command I have for this operating system is ps command, just like regular Unix ps command. You can see the process name here, and then you can, on the second column, you can see the PID for the process. The third column says the state of the process. You can see the shell has been running because it's a blocking process. So most often you see a shell being the running process and everything else is being ready. So I can kill the process 1, which is toggled orange. So if I press enter, the orange LED should stop blinking. So if you noticed, the orange LED is not toggling, but the yellow LED is toggling, and if you wait for a little long enough, the green LED also toggles. So I can do a ps command now, and what I do here is I mark the process 1 as kill pending, and then at the end I'll claim the resources. So I can kill the process 3 as well, and if you see, both the orange and the yellow LED stop blinking. So if I run the ps command, you can see both those processes are on kill pending state. So I can wake both the processes. First let's wake the process 1, and when I do that, you can see the orange LED started toggling, blinking again. Okay, similarly I can do for wake process 3, and then the yellow and the orange LEDs are also working. If I kill the process 7, it doesn't do anything because that's my shell process. I have a while 1 kind of in it, so that the process 7 will get killed. Okay, so I would like to just go quickly into the code just to see how I am doing the pseudo parallelism. So these were the 4 processes I was running. I was spawning from within my shell, from within my main program. Shell is one of the processes that I was spawning. So let's look at the spawn command. I go through a svc call interface, and which eventually calls the spawn system call for this operating system. And if you see here, I allocate a PCB node right there, and then I generate a random process ID. Well, this is not actually a random, it is a sequential process ID. I incremented by 2 every time I encounter it. And then I have the function name here. This function name is passed in as the 4th argument here, and then I use that to display my ps command. So then I allocate a stack, and then I start assigning values to the stack. So here what I do is, when I allocate a stack, I capture the high address of the stack, and then I start and then I use that as my reference to get the offset within that memory, within the stack memory. So, and this is where I'm building the stack. As you can see, I have the svc elect bit, then I have the registers as mentioned in the class. I assign all that, and then what I do finally, I insert the node in my circular linked list where the scheduler can pick it up. So that's my spawn process, which is pretty simple. Then this is my schedule process. So schedule process, as discussed in the class, has to push these two status bits, and then here is where the actual logic happens. So if you notice here, I save the current copy of the SP, and then whatever the current process that's running, I mark it as ready from running, so that I can pick it up the next time from the circular linked list. And then what I do is I look for the next job that's ready, and then I mark that job as running, and then I copy that job's stack pointer to the main stack, and then this follows the written code convention. Okay, this will actually change from a process to process, from one process to another. Now I have also have the other functions. Let's go look at the wake function. In the wake function, what I do is I find whatever the target PID that was passed in, then I make that PCB, that process, from within PCB I find the status for it, and then I make that as ready. So when the scheduler comes back, and since the scheduler is looking for the ready process, it picks it up and then it runs it. Kill command is very simple as well. I find a process for the given PID that's been passed in as a parameter. I'll mark it as kill pending, and so that will prevent the scheduler from picking that process and running. Okay, and all the other functions are pretty trivial once we know these functions. Okay, thanks a lot. That is my project, and I really appreciate your time. Thanks to Professor Jamie, Mark, and Daniel. Have a good day.